Hi there! Welcome to Palette University. So, today's my birthday! I'm turning 23 today, fun fact. And because of that, I wanted to do something a little bit special. So today's not going to be Pokemon related whatsoever, although if you notice, some things in the background, I did change up my set a little bit. Just I was kind of cleaning my room, and I had a bunch of Pokemon stuff up here, and I'm like, why is it there where only I can see it when I can put it in various places in my room? So let me know how you like. I mean, obviously, the posters in the back stayed the same, but like on top of my dresser, nope, wrong side. On the top of my dresser there, you can see my Rayquaza. I put my Pokeball Plus on top of its little box, and then my stuffed Arceus as well is up there. But today, like I said, not going to be Pokemon related. Today I'm going to be talking about some of the research that I actually do in my life as a scientist. It's going to be technical, but what I do is actually fairly simple. So I'm going to explain my research to you guys, and if you stick around to the end of the episode, there will definitely be a surprise. So definitely stay through to the end, because there's something pretty big, at least to me, and I'll explain at the end of the video. So stay tuned. So before we get into sort of the steps that I took for the actual research, I want to sort of define a couple of terms for you guys. Namely, they're going to be clade, latitudinal biodiversity gradient, the out of the tropics hypothesis, and that's pretty much it. So firstly, clade. A clade is really just any group of related organisms. In terms of what I do, I study paleontology, so an example of a clade would be dinosaurs, which is the topic of today's video. I studied a particular thing about dinosaurs, which we'll discuss in a couple of minutes. And within that clade of dinosaurs, so a clade basically can be a recognized group. So for instance, you could say primates. Or you could also say, a smaller group within primates, such as the homininae, which is all of our closest relatives that are no longer around. So it's everything more closely related to us than our closest living relatives, which are bonobos. So a clade is really just any group of living organisms. The second definition is latitudinal biodiversity gradient, and this essentially is just how different the diversity is at the equator compared to the poles. When looking at current biodiversity on our planet, as most people can pretty well guess, diversity is the highest around the equator. That's where the tropical rainforests are, that's where coral reefs are, which are two of, if not the two most diverse habitats on the planet. And then as you get more toward either the North Pole or the South Pole, diversity decreases. That's just a general trend that is very, very present in essentially every clade that you can think of. There are a handful of exceptions. But this has not always been the case, and my previous research that I've had published has been looking at this gradient through different blocks of time, which we'll be doing sort of today. Latitudinal biodiversity gradients are caused by several things, but one of the biggest contributors is climate. So when there's a strong climatic gradient, when the temperature at the equator is very different from the temperature at the poles, then you have a strong latitudinal biodiversity gradient. Whereas when the dinosaurs were around and there was no ice on the planet whatsoever, the latitudinal climatic gradient was much less severe, which led to a much less severe latitudinal biodiversity gradient. And lastly, the out of the tropics hypothesis. So this hypothesis states that because tropical areas are the most stable climatically because they don't have seasons, which, obviously I live at roughly 45 degrees north latitude, we have very severe seasons, as anybody who lives in, upstate New York can tell you. One day it could be 65, one day it could be, 32. You never know. And the difference between the high temperature and the low temperature in a year span is very significant. Whereas if you look at that same high temperature and low temperature at the equator, there's much, much less of a gap between those two temperatures. So between being more productive in that the equator receives more sunlight, it's warmer, so plants produce more energy, which is then put into the food web. So just in general, it's a hypothesis stating that because of all of these things, most clades originate in the tropics and then diversify into the higher latitudes. So the out of the tropics hypothesis has been pretty long-standing. I don't remember exactly who was the first one to establish this idea, but it really, in my view, the way I saw it, having studied latitudinal biodiversity gradients, it really only makes sense during times where there is a really strong gradient like today. In times like when the dinosaurs were around, diversity was at its highest, not at the equator, but at the mid-latitudes, but usually between 40 to 60 degrees latitude, either north or south. So I thought the idea that, things started in the tropics and then migrated, north and south just doesn't really make much sense when the mid-latitudes already just have so much more diversity at these time periods. So I decided to take a look at that. So I'm going to show you guys how. So all of my data comes from this wonderful resource called the Paleobiology Database. It's really just a fun website to play around on. I use this tab, but I'll show you just really quickly about the other side of the website, which you can literally just explore, like it says. So over here we have all sorts of these are examples of clades. So if we click on Mammalia, that shows every mammal fossil that has been published anywhere in the world. Alright, so let's look and see which, mammal fossils we can see. Let's just say in a place where I know that there's a good amount of mammal fossils, in Montana. So here we have the wonderful state of Montana, and it's neat because each of these little bubbles represents at least one collection, which, a collection is basically just somebody going out on any given day and, categorizing what they find. The bigger the bubble, the larger the collection, and the different colors tell you when it was found. So these green ones are from the time of the dinosaurs, which is really, really cool. And you can do that for literally any group that you can think of. So right here, obviously we're in mammals. If we look up the Dinosauria, here we have that same map of Montana, but with dinosaurs involved. And you can see some of these, Cenozoic is the current era that we are in. This is most likely talking about, oh no, it includes mammals still, so let's get rid of mammals. We don't care about them anymore. So yeah, here we have all sorts of stuff from back in the day. We do have some recent things, which this one here is, the O is highlighted down in the right hand corner. That means Oligocene, and I'm assuming that's a bird. Otherwise somebody is very mistaken. Yeah, it's a bird because birds are dinosaurs. Anyway, that's not really what I do. This is just a fun thing to come around and play on if you're interested in paleontology at all. So back to what I do. I go to the download data folder, and this is like heaven for me because this gives me access to information on any fossil that has ever been published. So what I did, for example, I looked up each of the major clades of dinosaurs. So you would think Theropoda, which are your things like T-Rex, Velociraptor, things that ate meat and walked on two legs. We have your Sauropoda, which are your long-necked dinosaurs, and so on and so forth. And if you just include all of them, and then you would click download. Oh, I spelled it wrong. Whoops. Yeah, so you would click out of them, and then you can select any given time periods that you want. If you only want, this weird 2 million year slice, if that's really all you care about, you can do that. If you want only fossils from Siberia, for some reason, you could do that in select by location. What I do is choose output options, because all I care about is the group. We want regular taxa only, because that excludes some weird fossils that I don't care about. And then down here in this area, you can pick the information, because this will spit out an Excel file at you. This gives you any information you would want. So what I look for is, let's see, we want classification, we want location, we want paleolocation, which location tells you where it was found today. Paleolocation tells you where it was at the time. Let's see. That should pretty much do. So, like I said, this will spit out a Excel file at you, and some of them can be quite large. So this is the theropod dinosaurs, which some people call Avitheropoda because it includes birds. But this is the actual data set that I was working with, and if you look here, records returned. We have almost 12,000 different rows here in this one spreadsheet, and I have 9. This is the biggest one, but I have 9 that all include the same data of different groups of dinosaurs. So, what do I do with this? How do I turn this giant mess of data into something usable and something understandable? Well, I just copy all of it, paste it in this other one, and take out the things that I don't really need. So for example, you know, the reference I don't really need. I still keep it in this big sheet so that just for posterity's sake. Things like phylum, everything's going to be the same phylum, so that's not really important. So I cut out all the other stuff, and I paste all of it here into just a different sheet in the same workbook. So in particular, what I was really looking for was the first appearance of each genus. So the genus, this thing right here is what most people know most dinosaurs by. So like Allosaurus is the genus name. Let's find another well-known one. Acrocanthosaurus is a pretty common one. Carcharodontosaurus, I actually have a tooth of a Carcharodontosaurus, just flexing a little bit there. Things like Tyrannosaurus, Velociraptor, Deinonychus, those are all genus names. So I want to find the first evidence of each genus in the fossil record. So I just select all of it, go to sort and filter, go to custom sort, and then right here I already have it pre-sorted how I wanted it. I just sort it by its classification first, just to make sure everything's neat in order, just as an easier way for me to figure out, you know, what each thing is. And then I sort it by max million years, which is the oldest occurrence of the unit that that particular fossil occurred in, because each one of these is a particular occurrence of a fossil. And then I sort it by genus. So let's do all of these steps together. Alright, so I have everything selected. So I'm just going to open up a new sheet, paste everything in here, and then we're just going to go through and get rid of the stuff we don't need. So I'll see you guys in just a sec after I do that, because the reason why I don't need it is a little complex, and most of the stuff is just kind of extra information that it just downloads automatically for you. So a lot of it's just not important, so I'll see you guys in just a sec. Alright, so the only things that we have left are the accepted name, which is the full name of each thing, its genus and its species. Some of them only have genus data, which is kind of a problem. So I'm going to show you guys how we kind of get rid of that in just a second. And as you can see right here, we have multiples of the same one. This is just different times that a scientist has found one of these species, Gorgosaurus libratus, out in the field. Right here we have max million years, which is the highest age of the formation, the rock formation, that this individual fossil was found in. The class, which, you know, class, family, and genus are its taxonomic ratings, and the paleolatitude. So first thing is we're going to select all this row. We're going to go to filter and sort, custom sort, and we're going to sort everything first by class, because there are some things here that we don't want, namely birds. This downloaded a lot of data for birds, which I don't really care about in this study, so I'm just going to select everything that is class Aves and just get rid of them. So as you can see, out of the around 12,000 that we had, we now are getting rid of about 10,500. So that automatically just narrows our data set down a lot. But that still leaves us with a lot of things that we don't need, like all these multiples of the genus Gorgosaurus. So what we're going to do is, again, select all of these rows, go to sort and filter. they're all already sorted by class, so we're going to add some levels here. We're going to sort them by family, sort them by mass million years, and then sort them by genus. And it's important that we go largest to smallest for max million years because we want the oldest one, which is the highest number, at the top of the list. So that went ahead and did it for us. So now, as you can see, all of these right here are of the genus Allosaurus. So all of these things we really don't want. We really do not want this. So what we're going to do now is select all this once again, go to the Data tab, and go to Remove Duplicates. What this does is allows you to check a certain area. For this, we'll be checking only genus, and this will check this column right here and only keep the first one that it comes across, which, because we sorted them by max million years, largest to smallest, will be the oldest one. As you can see right here, this one is 163.5 million years, whereas the one below it is only 161.2 million years, and they continue to get smaller from there. So if we click OK, it got rid of a lot of stuff and left us with 274 different genera and leaves us with the oldest of each one of those genera. So this is exactly what I did for each and every one of our 9 clades that we were working with. This one, I just kept a lot more of the data in. This is the actual data set that I used. I just kept a lot more of it in, mostly just for consistency's sake, because I kind of didn't realize that I was doing it until, 4 or 5 in, and I was like, well, I can't really change it now, because your methodology needs to, stay the same as you go. So let's take a look at the big list of all 9 of these clades compiled together. So this big old list right here with all these bright fancy colors is everything sorted. Here we have each of the 9 clades, or I guess I only had 8 clades. All of them together, and what I did was I sorted them by time and then by paleolatitude, and I also got rid of the negatives because in this kind of study, negative, which would mean south latitude, it's pretty much the same. It doesn't really make a difference whether it's north or south of the equator, just because we're just looking strictly at how far from the equator it is. So I sorted them by time, so young things at the top and old things, old things here at the top and then young things down at the bottom. And then I sorted them with lower latitudes first, going up to higher ones. But the way studies like this are done is you need to sort things into bins. So from the first one I found, the first oldest fossil, which is 237 million years, to the youngest fossil, which is 70.6 million years old. We found a time span of 167 million years. And I knew that I wanted 5 time bins, so I just divided that number by 5 and got 33.4 million years. So each set of these black lines represents 33.4 million years of time. As you can see, there wasn't a lot around for dinosaurs anyway at the beginning, and then as we continue to go on, things just get more and more, dinosaurs get more and more common and diversify a lot. So all I did was, after I sorted them, after I had them sorted in their time bins, and had everything color-coded, all I did was count, okay, so we have this type right here, the dark blue being a member of the Herrerasauridae, which are very primitive Saurischian dinosaurs, which are related to theropods, but not quite theropods. There's 5 of them in this time bin, and so one of them occurs in the low latitudes, and the rest occur in sort of mid latitudes, which I ranked by this scale right here. If it's 0 to 15 degrees latitude, it is latitudinal bin 1. If it's 15 to 30 degrees latitude, time bin 2, and that continues in 15-degree increments all the way up to 75 to 90 degrees, which is latitudinal bin 6. So that's exactly what I did for all of these time bins, and then I recorded ratios of these bins relative to each other. So, for instance, right here, the red represents sauropods, the big long-necked dinosaurs. There were a lot of them early on in the Mesozoic era. So I counted, there's only 2 things present in latitudinal bin 1. That's why there's 2 right there. Out of all these things in latitudinal bin 2, there are 12 sauropods, and so on and so forth, until I had ratios for every group, for every time bin, for every latitudinal bin. So right here, more different things appear. Here in time bin 4, we get also some more diversity. As you can see, theropods right here, very, very common in latitudinal bin 3, which is the lower mid-latitudes, so 30 to 45 degrees. Then in the last time bin, theropods were incredibly common in that same time bin, almost doubling in diversity between time bins 4 and 5. Similar thing with sauropods as well, very, very common in the upper tropicals, so 15 to 30 degrees, as well as 30 to 45 degrees latitude. So what does all of this really mean? Yeah, it's a lot of, pretty colors and a lot of numbers and fancy names, but what does all of this mean? So after I did all of that counting, I just went through and was like, okay, this right here represents the time bins, and this axis right here represents the latitudinal bins. So right here is like latitudinal bin 1, time bin 1, there was nothing for ankylosaurs, club-tailed armored dinosaurs. So I just went through and basically filled in each box and then created graphs out of them. So because there were no ankylosaurs in either time bin 1 or 2, or I guess very few in time bin 2, there was only 1 recorded, I created graphs out of them. So here we have graphs for every single clade in every time bin that they appeared. So as you can see, on the left, I'll just take you through a very quick example. We'll look at the late ceratopsian bin. So ceratopsians are things like Triceratops, the horned dinosaurs with the big frills on the back of their heads. If we look at down here being more toward the equator and 6 being more toward the poles, as you can see, they're much more common in the mid-latitudes than they are at the equator or toward the poles. And this is also the case if we look back through time. So once again, we're testing to see whether the out of the tropics hypothesis holds up, because it's well documented that the latitudinal biodiversity gradient at this time is very weak, unlike today. So, as you can see, the first time ceratopsians appear is in time bin 3, and they appear very strongly in only the mid-latitudes and not the tropics, as you would think if this hypothesis were correct. And then in time bin 4, they still really only occur in the mid-latitudes, still not at the equator, although they are starting to spread toward the poles. I would bet money that there were some present here, they just have not been, collected yet, because the odds of them being in mid-latitudes and then literally at the pole, but not in between, is very low. So I would guess that this is just a matter of sampling error. And then like we saw in time bin 5, which is at the very end of the time that dinosaurs were around, there's still none around the equator, but they've spread pretty confidently from mid-latitudes only to some of the higher latitudes. And this applies to literally every group that I looked at, with one exception, which were the pachycephalosaurs. Really the most well-known one, if you saw Jurassic World Fallen Kingdom, they're the headbutt dinosaurs, basically. They walk on 2 legs, they butt heads with each other. Rampardos, essentially, if we're thinking Pokemon. They only occur in time bin 5. They evolved very late in terms of dinosaurs, and they're present still not at the equator, which also sort of proves the point, but they're present basically everywhere else. But probably the best evidence of this out of the tropics not being corrected are the theropods, as well as the sauropods. So we can look at them both together. Both of them show very early in time bin 1 that they are in mid-latitudes, and that's pretty much it. There's nothing toward the poles and nothing toward the equator. Time bin 3 is the only bin where they occur. Or latitudinal bin 3 is the only bin where they occur. As we move toward time bin 2, they sort of spread from latitudinal bin 3 into latitudinal bin 2, and in the case of the sauropods, a little bit into latitudinal bin 1, which is literally right at the equator, and sort of as well into polar regions in the terms when we're looking at sauropods. Looking at time bin 3, we see once again very strong mid-latitudes and very weak low latitudes and poles. So all of this is suggesting that they originated in the mid-latitudes and then spread away from them, as we see with the theropods, where they do sort of make it toward more polar regions. They never really do super well at the equator. There's a handful in time bin 4 that are around the equator for theropods, and then sauropods sort of do sort of well at the equator for a while and then kind of tend to die off, but they never really do so well at the poles. Now, granted, all of this is a rather low sample size, all things considered, even though, you know, there were 274 genera just of theropods that we used. That was by far the biggest amount. I would say the only one close would be sauropods, but, you know, pachycephalosaurs, there was, what, let's see. There was 1 plus 4 is 5, plus this 5 is 10, 12, so there were 13 total, so that one's not exactly reliable. But specifically theropods and sauropods, very clear data in my opinion. I've not run any statistics on this to see how significant this trend is, but if I had to just guess, which is not really something you should do in science, but for the sake, this is all just for a research paper, this isn't really like anything, you know, being published, but I would say that this will hold up statistically. And that's pretty much it. This all, you know, all things said and done, took me roughly, you know, 7-8 hours to do this analysis. Like I said, did not run statistics on it. I would like to at some point. That will depend on whether my teacher for the class I'm writing this paper for feels that I need to. Sometimes he just likes to make me do extra work, but that's just college sometimes, I guess. But yeah, that's pretty much how the science that I do works. This is what I do on a semi-regular basis. Not all the time, but this is what a lot of modern science, particularly in the field of, you know, ecology and, you know, people who study evolution patterns, this is what people do every day. They probably have fancier tools than Excel, but this is pretty much what real scientists do. And as you can see, it's really not that hard. That's one of the things that I love about science, is that this is something that, you know, if you know, take the time and rationalize things out, this is something that really anybody could do. And this is potentially, you know, I don't want to say disproving, because science really doesn't prove or disprove things. It's just a way of providing evidence for or against an idea. But this provides evidence against a pretty long-standing idea when it comes to, you know, modern biodiversity patterns. So with that, I guess I'm not going to make you guys wait any longer for the surprise, so here we go. This is real. This is, I shaved my head. So little personal now, but I've always been, you know, I've had a receding hairline literally for as long as I can remember, ever since I was probably like 16. And back in high school, my friends used to, you know, pick on me for it, like lovingly, but even though I knew they were joking, it still kind of hurt a little bit. It's one of those things, everybody has one of those things that they're just super self-conscious about. And so I planned on just shaving my head over the summer. I moved into a brand new school, you know, that whole, you know, starting over shtick. And I was like, I just plan on doing it over the summer. Nobody's gonna know any different. You know, people, when I post something on social media, would be like, whoa, Gavin shaved his head. But they'd get over it, because I don't see most of the people that I have on social media in real life anyway. But then my job is doing something really cool in that they're offering like professional headshots, like headshot images, to use for, you know, your professional social media, because, you know, they're trying to set us up to be, you know, successful professionals in our lives when we get out of college. And I was like, do I want to, because obviously I want to take this opportunity. I'm not just going to have this offered to me and not take advantage of it. But do I want to have pictures taken when I have hair only to shave my head in like a month and a half and have them be essentially useless because I look so different? No. So I kind of worked myself up to it, and then yesterday I shaved my head. It's weird when you just when I word it that way, and that I just casually shaved my head yesterday. But here we are. A lot of people have told me that it looks really good, and there are people that, you know, the kind of friends who would tell me that if I look weird, and I still think it looks a little weird, but that's just because I'm staring at myself right now, so I'm sorry I'm not looking at the camera, because I still think it looks weird. But it's just something that I'm going to get used to. I think overall I like it. It's definitely going to be different. Yeah, I don't really know how to end this video from here, so I'm just gonna send it out. Thank you guys very much for watching. If you enjoyed this video, and seeing what the inside life of the more data side of science is, definitely let me know. Feel free, I'll leave the link to the paleobiology database down below. It's actually really fun to just pick out like your favorite group of extinct animals and see, oh, you can just walk out and find these in the ground in these certain spots, which is nice because I'm moving to South Dakota in August, and there's literally just dinosaur bones sticking out of the ground if you know where to look, which I think is super neat. But yeah, definitely follow us on Twitter as well at palette_u, and as always, there's a time and place for everything.